Good afternoon, everyone. Welcome back to day 2. So, yesterday we had looked into what we mean by security. Now, here, when we are talking about security, we are talking about financial securities. All right, financial securities are any sort of financial holdings that have monetary value. All right. So now today we'll move forward and we'll take a look at something we called CRISP MLQ, that is cross industry standard practice for machine learning with quality assurance. This Q is the main part. You're looking to ensure the quality. Now, if you ever Google these things or if you ever do your research, you'll find that around 70 to 80% of all ML projects fail because there is no proper way, there is no proper methodology that is being followed. Okay, most of these projects are taken up in a very cluttered manner. Okay, and because of that clutter, there is no organization, and due to the lack of organization, these projects fail. So now in the industry, it is standard practice. It is an accepted practice that whenever you take up an ML project, you follow this methodology. Okay, you follow the standard practice. This is standard operating procedure wherever you go. It doesn't matter what company you're going to. Maybe they might use some different type of, some different type of standard practice. But there will be some set standard that you will always have to follow within ML. It doesn't matter if the company is a MNC or it's a startup. This is the expected method. Okay, so now we'll take a look at CRISP MLQ and what sort of analytics we are applying. So first, we'll take a look at stages of analytics. What are the different stages of data analytics? Data analytics is an important part for any data scientist. All right. Then we'll take a look at the CRISP MLQ methodology. And afterwards, these last 3 bullet points, they deal with machine learning models. We'll take a look at how we are making our machine learning models work. All right. What are the different ways in which you have machine learning models? What are the different sort of error functions? And what do we mean by underfitting and overfitting? Okay, so let's start. So you have 4 stages of descriptive analytics. Okay, so we have 4 stages of descriptive analytics. What are these 4 stages? These 4 stages are what we call as descriptive analytics, diagnostic analytics, descriptive, diagnostic, predictive, and prescriptive. Each of the name means something, and we'll be taking a look at what that name means. Okay, so here we have the 4 stages of analytics. So descriptive analytics. In this, we are trying to figure out what has happened. You are given some data. You have historical data of some outcome and you're trying to understand why did that specific outcome happen. For example, if you take a look at the 2008 US housing market crash, so if you take a look at this data set, if you have this data set available with you and you do an in-depth analysis on it, you will realize that the main reason why this happened was the banks were approving any and every loan. All right, they were approving any and every loan. That means all you had to do was go to the bank and say, hey, I want a loan, and you'd get that loan. That's it, nothing else. All right, so that is what we will find out in stage 1. Then you're taking a look at diagnostic analysis. Now you can say, why has it happened? Why did this happen? Why did this specific thing happen? It's because of, you can say, maybe lax regulations. The housing loan market wasn't properly regulated. So the banks, they took advantage of it. They only cared about how many loans they were sanctioning. They did not care that if they were sanctioning a loan to a person who could afford to pay it back or not. All right. So in stage 2, we are trying to understand what has happened. Then we come to stage 3, which is predictive analytics, where we are trying to predict the future. Now, this 2008 market crash wasn't a surprise. A lot of people were predicting that something like this would happen. And they were following predictive analytics. They were predicting the future. They were saying that the way the market is structured, the way it is moving forward, there is no way we don't get into a crash. There is no way the bubble doesn't burst. There is no way we don't hit recession. Similarly, the same thing is happening right now. In 2022, again, if you look at USA, it is heading towards recession. And the problem with a country like USA heading towards recession is that it affects the entire globe. With them being the most important financial power in the world, their influence is very high. So as a result, this has also been predicted because inflation has gone crazy. Inflation has gone up very, very high. You have, like, there is an expected level of inflation. Most economists you would talk to, at least economics who are worth their salt, they would say that maybe 1 to 3% inflation is good. This means that there is scope for your economy to grow into. Of course, you will always have time when you'd have deflation. But normally, if you have a little bit of inflation, that is good. The problem is when you start hitting 10% inflation or 15% inflation. When you start hitting these numbers, that's when you start running into problems. All right. So the same thing is happening in USA. You have inflation rising. At the same time, you also have unemployment rising. So that means more people are out of the market. It also means that the purchasing power of people who may still have jobs or who may still have the finances is going down because of this inflation. And whenever you have this threat looming about anything like recession, you have people start becoming more and more careful. They start spending less and they start saving up more. And as a result, there is a decrease or circulation within the economy itself. Okay, so that's when you end up with this situation. All right. So in order to avoid a situation like this, data scientists who have been working on these problems, or any other economist who has been working on this problem, they would come to stage 4. After making the predictions, they would come to stage 4. In stage 4, you tell what should be done. You would give some suggestions. Maybe you would suggest that, hey, the central bank can lower the lending rate, allow people to lend more money, allow businesses to take bigger loans to get more money circulated in the economy. Maybe the government can announce subsidies on essential products. Because of inflation, the price is going very high. So you can start, suggesting that, hey, what we'll do instead is, instead of giving people money or reducing the loan and the credit rate, what we'll do is, instead we'll simply ask people, we'll simply tell people that, we'll subsidize your products. If you were paying $4 2 years ago and now you're paying $6, you'll continue to pay the $4 and the government will pick up the tab for the other $2. So that is how you offer subsidies. This will incentivize the people to go back to their normal spending habits, pre-recession threat spending habits. All right. So these are the 4 stages of analytics. Okay. So we can use these 4 stages for any sort of prediction. So these 4 stages play an important role within machine learning itself. Okay. So moving forward, we have CRISP MLQ. Now CRISP MLQ has 6 stages. Stage 1 is business and data understanding. In business and data understanding, you try to understand what is your business objective, what is your business problem that you're facing. Okay, whatever business problem you're facing, you try to understand that. Then you also try to understand the data. Data understanding is very important, because if you're not able to understand the data, it just means that you don't know what you're going to do, because data can be of different types. And for different data types, you have different types of ML model that you need to apply. So here, you could have categorical data, you could have continuous data, discrete data, quantitative data, qualitative data. So data has to be of different type. And because it is going to be in different forms, you need to fully understand the data before you can move forward to the next step. The next step is data preparation. This is where we perform something we call EDA, that is exploratory data analytics and pre-processing. Okay, pre-processing. Pre-processing is cleaning up of the data. These 2 things we will cover in tomorrow's session, so we'll not spend too much time on them right now. Okay, so you will cover EDA, you will cover pre-processing, you will also do something we call feature engineering. Feature engineering means manipulation of your features to improve the performance of your ML model. Okay, and then you come to stage 3, that is model building and tuning. Here you're building your ML model. So once you build that ML model, then you try to see, is this ML model fitting our requirements? If it is fitting our requirements, then you move forward. Otherwise, you get into tuning. Tuning is changing the model parameters in such a way that it is improving the model performance. So we do something we call as hyperparameter tuning. Okay. So we tune our model and we keep repeating these steps until we get the results we want. That is, so it's a cyclic step. So here you can see, first you understand the business, then you understand the data. If you don't understand the data, you go back to your business. You try to re-understand what is happening in the business. All right. So without understanding business, the business problem, you cannot understand your data. Without understanding your data, you cannot proceed to the next step. That is where you're doing EDA pre-processing and feature engineering. Now here you start a cycle. This keeps going like a cycle. Okay. So you start with data preparation. Then you do model building. Then if your model building is not giving you the results you need, you go back to data preparation, you do feature engineering, you do hyperparameter tuning, you do all sort of things, you do cross validation. Afterwards, you come back to your model. Again, if the model is not giving you the correct result, you go back to your data. You do more things, you try different things. So up until your data is giving you the accuracy you need, you keep repeating, you keep moving in this cycle. Okay. The reason why is, like, for example, you build your ML model for predicting stock price movement. Okay. So you're trying to predict the stock price. If your accuracy is 50%, you'll not just say that, hey, just take every other prediction my model is making and bet on it. No, you go back to your step 2. You go back to your step 2. You come back again. The next time you'll notice that the performance has gone up by 65%. Again, better than the last performance, but still not good enough. So you go back to step 2. Next time you notice 85%. This is much better. 85% is quite good. But then again, you go back to step 2. And then you get 90%. Again, you go back to your step 2. Afterwards, you notice it has gone to 88%. So after going back from here, you don't go back to your step 2, because this is where your parameters are the best. At these parameters, you're getting the highest accuracy. All right. So here you stop, you say, I'll take these parameters and I'll move on to my next step. The next step is testing and evaluation. You're evaluating the model performance. You have trained your model, you're getting some accuracy, and here you're evaluating how you're getting that accuracy, how accurate it is. Is it suitable for the business problem you're dealing with? You can also take a look at if it is suitable for the next business problem you might be facing. Okay. After this, you move on to deployment. Deployment is deploying your ML model on some UI. Okay. Now, if you have a client who's not tech savvy, you cannot send him the entire ML model and say that, hey, this is the model, install these libraries, run the model in such a manner every time you want a prediction. No, you want them to have easy access. You want them to have easy access. Okay. And since you want them to have easy access, you say, what I'll do is I'll build you some UI, or I will host my code on your UI. At the same time, whatever code you have written is your intellectual property. It's your IP. So you also want to protect it. You might have come up with a groundbreaking technique that other people are struggling to implement. So in that scenario, you don't want your code to be available to everyone. So you just secure your code and then you just give the information through a UI. And once you deploy the model, then you get involved in monitoring and maintenance. You are monitoring how that model is performing. What happens if there is some changes in the data? How is the model adapting to those changes? Okay, so you're evaluating the model performance at the user end. This is not at your end. This is at the user end. Okay, so here you do that, and then you can also perform maintenance in your model. Now, there might be some updates to the libraries you're using, to the packages you're using, that cause your code to break. So in that scenario, you go back, you repair those issues, and you redeploy your code to the UI. Okay, so this is monitoring and maintenance. Okay, so these are the 6 steps of crisp MLQ. And if you want to build a successful ML model, you have to follow these steps. That's just as simple as that. Similarly, you have these data sources. These data sources are where you are getting that data from. These data sources could be some RDBMS. That is a relational database management system like your MySQL. So you have the data in SQL. You can extract the data from there. You might have data in your local system. You might have collected some Excel sheets, okay, based on your own understanding, based on your own analysis. You might have CSV files, Excel files, text files. So data can be of these types. You might also have NoSQL servers like MongoDB. Okay. You can also get your data from the internet. So data sources can be many. And depending on your use case, you might be actually using one of these data sources. Okay, so within data sources, we have 2 types. We have primary data sources and we have secondary data sources. So primary data sources is what? Primary data sources is where we have own data. You're collecting some data on your own time. And secondary data sources is data that is already available. Okay, so primary data sources is when you're collecting the data. But when you start working with ML, you will always start off with secondary data. Secondary data is pre-existing data. So first you will work with the pre-existing data. You will see if that pre-existing data is going to work or not. And then you move on to primary data if you need. So primary data can be surveys, online form, IoT sensors. So primary data sources can be of any type. Okay. So this is crisp MLQ methodology. So this is an important methodology. And then moving forward, we'll take a look at what we call as ML primer. Now, within ML primer, let's go back here. So within ML primer, you have 2 types of data. You have unsupervised and you have supervised. So there is a big difference between the two. In unsupervised, Y here is an outcome. Y here is our outcome. This Y is unknown. So we don't know what the y is. We don't know what the output is. We have some data set and we are trying to find some patterns within that data set. And then you come to supervised. In supervised, y is known. You already know what the final output was. No matter how many features you are taking, you could be taking 2 features or you could be taking 100 features. It doesn't matter. You are still having this. You are still having the output. You still know what the output is. So that is the big difference between the two. And because we have this difference between the two, the way we train and the way we build our ML models within unsupervised and within supervised learning are completely different. So you start diverging here. You start diverging into 2 different sectors. So this is our unsupervised learning model. So in unsupervised learning model, we are taking the historical data. Now historical data is the pre-existing data. So this would be your secondary source. And within this historical data, you are applying some ML model. Okay, so you are applying some ML model, and based on that ML model, you will get some rules or some patterns. Now these rules or patterns, what they mean is it will define how the data is going to behave in the future. Now here you don't know the output, obviously. So that is the big thing. We don't know. Y is unknown. So we are in the blind about the Y. We don't know what the output could be. It could be anything. It could be any one of the features, but you don't know. So what you're doing here is you're taking the data and you're trying to make sense of that data. You're trying to see how we can take this specific data and we can, understand how the data is moving, how the columns are affecting each other. What happens when one column goes up? What happens when the other column goes down? So all these things, we are trying to make some logical sense. So that is where we are making these rules and patterns. Once you get these rules and patterns, you take these rules and patterns, you get some new data. More data has been generated since the last time you took the data. So you take this new data, you apply these rules and pattern on them, and you get your predictions. These predictions are basically prediction on how the data is going to move in the future. What can you see? What is likely to happen based on the historical data, based on how this specific data has been moving on so far? What is likely to happen in the future? So that is prediction. So this is what your unsupervised workflow looks like. And then moving forward, we have supervised learning. Now in supervised learning, first thing we already know is that Y is known. That means we know what the final outcome is going to be even before we have started working on the data. So instead of taking the full data, here what we do is here we do splitting of data. In splitting of data, within supervised learning, you can say you're splitting the data into 3 parts. You're taking the training, you're taking the validation, and you're taking the test. Okay. So now, for example, here you have 10,000 entries. you decide to take a simple random sample of 8,000 of them. So what you'll do is you'll train your model on 6,000 and you'll train you'll validate your model on 2,000. Now, of course, this validation value is not standard. It can keep changing. You know, you could also be taking half and half. You could be taking only maybe 500 to validate, you know, so that is up to you. That is your choice. Okay. But we do this validation step for a very important reason. Okay. So what is that reason? You take your training data and you are applying some ML model on it. Okay, you are applying some ML model on it. Now this ML model will generate some mathematical equation. It will generate a mathematical equation. This equation will solve your problem. For example, in linear regression, which is a supervised learning technique, you're generating an equation that looks like y equals to beta naught plus beta 1 of x. So you are generating this equation. This equation will give you solution for all the problems you have that are related to linear regression. Okay. So after generating these mathematical equations, you take these equations and you send it to your validation data set. What this validation data set will do is it will try to validate these results. It will see how accurate that mathematical equation is. So for example, you do this training data set, you get that equation, and then when you do the validation, you see you're only getting 60% accuracy on validation. That means your equation is not very accurate. So when your equation is not very accurate, we do what we call as hyperparameter tuning. So we are tuning these hyperparameters. We have some hyperparameters that are affecting the model performance. So we are tuning them. Okay. So after tuning these hyperparameters, you try to increase your validation accuracy. You keep again in this loop. We have already covered this loop where we are trying to get the highest possible accuracy. So we have already covered this loop, but we are going through it again. Okay. So tomorrow, so here you keep working on it until you get a good validation accuracy up until you get 90% accuracy, for example. After 90%, you are seeing that no matter what you do with the hyperparameters, no matter what you work on the data set, the accuracy is not increasing. So there you stop. And then you get the outcome. This outcome will be your final equation. This final equation would be the best fit equation for your ML model. All right. So you're taking this final equation. Now we have 10,000 entries. We have used 8,000 entries. We have 2,000 entries left. Now, if you know that you will get new data, you can maybe even use all 10,000 entries in this step 1. But here we are using this historical data. So this can also be called as test data. So within this test data, you're trying to apply this mathematical equation and you're trying to get the outcome. But you might think that, hey, we already know the outcome. Yes, we know the outcome. That is correct. But because we know the outcome, that means we can compare our ML model outcome to the actual outcome, and we can get some accuracy values. You can get the accuracy here. You can get the accuracy here. You can also get the validation accuracy. So you can have 3 accuracy measures. You can also take a look at error rate. Error rate is how much. So if you have some actual values minus the predicted values, error is showing that how much are your predicted values deviating from the actual value. Okay, what is the difference? What is the error? So when we do that, we get the error rate. So we can calculate the error rate, we can calculate the accuracy rate, we can calculate how much data we are losing at each step, because every time you iterate through these steps, you have some sort of data, you're losing some sort of data, or you're getting rid of some sort of data. Okay. So we can calculate all these values. Okay. So this is our machine learning algorithms, supervised and unsupervised. So now, before we move forward, a quick thing that you should know for the next step, we have data types. We have continuous data and we have discrete data. Continuous data is data that can be represented in decimal form. And when you're represented in decimal form, it is making some sense. And discrete data is the opposite of continuous. So that means here you cannot put the data in decimal format. For example, if you're taking a look at the number of clients a company has, you cannot have half a client, or you cannot have a quarter of a client. You either have the client or you don't have the client. Okay. So this is where we end up. So within discrete, we have something called categorical data. Categorical data is non-numeric data. Okay. That means this data is not represented in numbers. So just a quick FYI. Moving forward, this is our data split. We are using this data splitting for predicting the model accuracy. So we are evaluating the model. So you have training. You keep validating the data until the desired accuracy is achieved. Now, maybe you feel like 89% is good enough accuracy, but your client is insisting that we want 95% plus. So in that scenario, we have to keep doing this. On validation, we are testing the data, testing the train results again and again until we find the best performing algorithm. We find the best performing mathematical equation. Once you do that, you combine these two together. So again, going back to our previous example, you have 10,000 entries. They were split up into 8,000 and 2,000. And then this 8,000 was split up into 6,000 and 2,000. So after you get the desired accuracy, you go back this way. You go back to this 8,000. You train the model on these 8,000 entries. and then you move towards your test data. Why? Because you want your training data to be as big as possible. You don't want your training data to be small when it is possible for you to take bigger data set. But at the same time, you have to ensure that you are not, having the data to, you're not having this data, what do you call it? Too large. You don't want that to be so long that it is taking days for your machines to compile the model. Okay. So after you do that, you check for overfitting or underfitting. So we'll cover these topics in a little bit. Now we move on to the testing. On testing, we are testing the accuracy on new data. This is the data that the machine has never seen before, that the ML model we have built has never seen this data before. So in terms of that, we can call it as new data. Okay. So here we are trying to get test error and accuracy. We are trying to see what is the error and how accurate our predictions are. Okay. So we move on. So moving on, we have error functions. Error functions are used to calculate what is the error rate. So the first error function is something we call as the confusion matrix. And this is used when our output is categorical. Okay, when you're dealing with categorical data, you make the confusion matrix. So within the confusion matrix, you have true positive. Now here we are taking a look at cancer patients. So the output here is, does the person have cancer? Yes and no. Okay, or you can say it is true or false. But it is categorical. So here we have 4 quadrants. This quadrant true positive means, it means that person who had cancer was diagnosed as having cancer. Then you have true negative. True negative means the person who did not have cancer was diagnosed as not having cancer. Then you have false positive. False positive means the person who did not have cancer was diagnosed as having cancer. And then you finally have the false negative. False negative means the person who had cancer was diagnosed as having no cancer. Okay. So this is a confusion matrix. Within the confusion matrix, we can calculate the accuracy. Accuracy is the correct results. That is these two values divided by the sum of total number of samples we have taken. If you have taken 500 samples, you divide it by 500. If you have taken 10,000, you divide it by 10,000. And then you can also calculate the error rate. The error rate is these wrong results divided by, again, the total number of samples you have taken. So this is the basics of a confusion matrix. Now, this is not all that we cover within the confusion matrix. We also have a few other evaluation metrics. The first one we have is what we call as precision. Precision is checking how accurate the predicted positive results were. That means whatever the scenario may be, you had predicted these results would be positive. But here you're saying that how accurate those positive results was. So the formula is quite simple. You take the positive results that were actually positive, and then you divide it by the sum of all positive outcomes you had. That includes the false positive results. Regardless of whether it was correct or not, it is still positive result. Sensitivity is checking to see how many people who were actually positive were also called as positive. So when you have false negative, that means you have people who had cancer and they were diagnosed as not having cancer. So you end up with true positive divided by the sum of actually positive outcomes. Okay. So the sum of actually true outcomes. And then you finally have the true negative rate, where you're checking how many people who were actually negative were also predicted as being negative. So you take the true negative and then you divide it by the sum of all negative results in your sample. So you end up with these three equations. You have precision, you have sensitivity or recall, and then you have specificity. So then you have two types of error. These errors are called alpha or type 1 error, which is basically how many false positive results you had. This is 1 minus specificity. Okay. And then you have the false negative rate, which is 1 minus the sensitivity. So here you're testing how many times you had wrong results within the positive and the negative class. And finally, you have the F1 score. F1 score is taken like this. It is 2 times precision by recall divided by precision plus recall. This defines, this matrix is used to create a balance between these two positive outcomes. Okay, precision and sensitivity. All right. So this is confusion matrix. And then we have the error function. Error functions are used when this y is continuous. Okay. So within error function for continuous variables, we have 6 types of error function. The first error function is mean error. That means you're taking the mean of the error. So anytime you do the calculation of accuracy plus error, you're getting 100%. That means accuracy plus error should always be equal to 1. Okay. So now here we are calculating the mean error. The mean error here would be this plus this plus this. 1 minus 1 plus 1 minus 1. 0. Same thing here, 0. What is mean? Mean is the sum divided by total number. So 0 divided by 4 is still 0. So mean error here would be 0. Does that mean that you have 0 error? Absolutely not. It means you're getting 0 error. Then you take the mean absolute deviation. Now mean absolute deviation, you're taking the deviation of the error and you're trying to calculate the absolute value. Okay. So here you're calculating the deviation, the standard deviation, and you're subtracting it from the error and you're taking the absolute value. Absolute value would convert these negative values into positive values. And then finally, you have the mean squared error. Now in mean squared error, you're taking the square root of these errors. So you take the square root of this, you get 4 by 4, 1. Okay. And if you take the square root of this, you get 100. Okay. So the mean squared error is 1 here and 100 here. Okay. But when we are working with larger data sets, mean squared error can become really big depending on how big our variables are. So what we take is the square root. Root mean squared error. This is where you're taking these error functions and you're taking the square root of them after doing the error function calculation. Okay. So this becomes 1, this stays as 1, and this becomes 10. Now 10 is a more accurate representation on what the error is. Okay. And then finally you have the mean percentage error. In mean percentage error, you're taking the actual value that you got, you're subtracting it from the predicted value, and then you're dividing it by the actual value. So you will get the percentage difference between the actual value and the predicted outcome. So here you get the answer in percentage. But again, what happens when predicted value is greater than actual value? Then you're getting negative percentages. So when you're adding negative and positive percentages, you might be getting some sort of error that is not the correct representation of what the error actually is. So what you do here instead is, again, you take the absolute value. Now we particularly don't care if it is predicting higher than the actual value or lower than the actual value. We are currently only focusing on what the error is. Okay. And the error is this. So you end up with mean absolute percentage error, or MAPE. So these are the 6 error functions that you might come across when you're working with an ML model. Okay. So then we move forward. We have underfit versus overfit. Now, before we get into underfit versus overfit, let's take a look at normal fit or good fit. So good fit is when training error is low and test error is also low. This means that your model is giving good prediction. It is fitting the data set very well. Okay. So finally, we have overfitting. Overfitting happens when training error is low, but test error is high. That means your model is performing good on your training data set, where it is learning the patterns, the rules, it is getting the mathematical equations, but it is not performing well when you're dealing with test data. Okay. So this is what we call as overfitting or variance. And in order to fix it, we use something we call as regularization techniques. So these techniques help us to deal with overfit. And then you have underfit. Underfit is when training error is high. Now, if your initial step is just wrong, when you're making this much of when you're facing this much of a problem in the first step, why would you go to the next step? Why would you even care about going to the why would you even care about going to the test data? So then we go for underfit or bias. So in this scenario, to fix it, you either want to, add more data, okay, or you want to do better feature engineering, or you can do a combination of both. So this is underfitting and overfitting. Now, if you're dealing with balanced data means where the outputs are somewhat balanced. You split randomly to avoid bias. That means you want your balance to be maintained when you're splitting into train and test. You can take 60% into training, 20% into validation, and 20% into test. And then you can combine this 60 and 20% to form the training data set. Okay. So large test set. You have a sufficiently large test set. So if you have 20,000 entries, you have 4,000 data points. So this will predict more accurately what is your error rate. Okay. So again, this is, you can take 80-20, but you can also take 90-10 or 70-30, depending on the scenario. Depending on your scenario and your business case and your personal preference. Okay. So that is overfitting. In overfitting, statistically speaking, it happens when there is too much data that the model is started to pick up on the noise. Noise is the junk information, and it is getting confused because it is getting an information overload. Okay, so when that happens, we say we are facing with overfitting. So here, this is what overfitting looks like in classification. It is predicting, it is taking this junk values as well, or this. Okay, so these are overfitting. And here you have underfit. That means underfit is when the machine learning algorithm cannot capture the trend. There is some trend in the data set. The machine learning algorithm cannot capture this trend. And because it is not able to capture this trend, we are getting this inflexible data. Okay. So this is what happens when you're dealing with underfitting. So this is your good fit, where the model is not fully accurate, but it is accurate enough for us to move forward. Okay, so that is overfitting and underfitting. So with that, we come to our session. So thank you everyone for joining, and tomorrow at the same time, 5 p.m., we'll start with EDA pre-processing. All right. Thank you guys.